All right, this is the unit review for the periodic table exam. All right, so the first question is asking how is the modern periodic table arranged? Okay, there's many ways you can answer this. All right, first thing, let's take a look here at the old periodic table. So it could be talking about just number one. All right, these vertical columns, these up and down things, these are called groups or families. And then we have these horizontal rows going this way. So, and these things are called periods. So there are 18 groups, 1 through 18, labeled right here, 1 through 18. And then there are 7 periods. Okay, so 1 through 7 going down the side here. Notice these 2 rows at the bottom are inserted here. So they're parts of the 6th and the 7th period. The main thing it was asking, though, it was looking at like classes of elements. Okay, so once again, you can look over here. So everything here that is highlighted right now is what's considered a metal. All right. So that's everything to the left of the stair step with except hydrogen. Okay, we have metalloids. These are those things touching the stair step. Recall, if you say aluminum or polonium, I will also count those as metalloids because they are touching the stairs. But I think you guys know like aluminum for certain is metallic. And then over here we have nonmetals, so everything to the right of the stair step line with hydrogen. All right, so that's largely what it was looking for: metals, nonmetals, and metalloids. Let's see. Number 2, which of these sets of elements have similar chemical and physical properties? Well, the thing you have to recall, in order for things to have similar chemical and physical properties, they have to have the same number of valence electrons. You'll remember from the previous unit, elements in the same group or family have the same number of valence, so we need to look and see which one of these groups have are in the same group or family. So if we look at this, it's these right here, the ones that are in group 2 from that list. The first grouping, they're all like along here, okay? Now, granted, some of those in that first grouping are going to be non-metals, but then you have boron, which is a metalloid, and I think that last group is simply ones that start with N. So yeah, strontium, magnesium, calcium, beryllium, all members of group 2, all have 2 valence electrons. B is the best answer. Okay, metalloid or non-metal. So basically we have to find where these elements are in relation to that stair-step line. So the first one we have gold. Here's gold. Gold is definitely a metal. Next one we have silicon. Well, silicon is right here. It's sitting right on top of the stairs. Silicon is a metalloid. Sulfur. Sulfur's right here. Okay, definitely to the right of the stairs. Going to be a non-metal. And then lastly, we have barium. Barium right down here, definitely a metal, definitely to the left of the stair step. Okay, so now we're to identify the following as either being more characteristic of a metal or non-metal. So gases at room temperature. So how you can tell states of matter when you look at the periodic table, you're going to notice here there's a key. Okay, if anything solid is printed in black, anything that is liquid is printed in blue, anything that's a gas is red. And then if it's unknown, it's because they're synthetic. They didn't make very many of those atoms. They're just kind of grayed out, which are like these ones down here in this bottom row. Okay, so we're looking at gases at room temperature. So we're looking for the ones printed in red. That's largely these over here. Okay, these are gas, these are gases. Okay, so that is definitely going to be a non-metal. Maybe I'll try out non-metal. Okay, brittle. Okay, brittle is the opposite of malleable. Malleable means you can pound it and it bends into different shapes, pounds into thin sheets. Brittle means you hit it with a hammer and it shatters. Okay, that as well is going to be a non-metal. And as I was just describing, malleable means bendy or you can shape and form it. Well, that is one of the properties of a metal. Poor conductor of heat or electric current. That's going to be nonmetals. Nonmetals are not very conductive. Okay, metals are great conductors. Shiny, and another word for shiny is luster. Okay, that's the scientific name. That is the property of a metal. Okay, so those are all metals and nonmetal properties. And then if you have a metalloid, metalloid has properties of both. Okay, and so like in a classic example, silicon is a metalloid. I showed you silicon in class. Silicon, definitely shiny, okay, but it's brittle. Okay, so it's lustrous, so like a metal, but it's brittle like a nonmetal. It does conduct electricity a lot better than nonmetals, but not as well as metals. So once again, kind of an in-between type deal. And you would expect them to have kind of in-between properties because when you look at the periodic table, there are the metalloids. They lie in between metals and nonmetals. Name two elements that have properties similar to that of sodium. So let's take a look at the periodic table. And you have to recall, okay, if they have similar properties, that means they're members of the same group or family. So sodium's right here. So it's really any of these. The only one I wouldn't include would be hydrogen, okay, because hydrogen is not a metal, right? So hydrogen's kind of unique. It sits over here, but it's not really like these other elements. So lithium, potassium, these would probably be the two closest, but these would have similar properties as well. So the closer they are to each other, the more similar their properties, but they have to be in the same vertical column. So lithium and potassium would be probably the best answers. Arrange these elements in order of decreasing atomic size. Okay, and so when we're talking about atomic size, we're talking about like atomic radius. All right, and we're going to see, does it demonstrate a group or a period trend? So real quick, let's talk about atomic radii. Okay, and we've talked about this before. All right, so going down, the atomic radius will tend to increase. Why? Because every time you move down one of those rows, you increase the size of the atom because you get more shells, right? So here's the nucleus, here's the first energy level, the second, the third. As you add rings, the atom gets bigger, right? So going down a group, the atoms get bigger. Going across from left to right, they get smaller, okay? And so at first, this doesn't make a whole lot of sense. You're like, well, that's kind of confusing because, as you go across a period from left to right, the atomic number increases. So that means you have more protons, which means you have more electrons, which means you have more neutrons. And usually when you add more stuff, things get bigger. However, going left to right across the period, they get smaller. And the reason for this is that the number of protons is increasing. They have a larger centralized positive charge. They pull the electrons closer to the nucleus. And so left to right, they get smaller. So we need to look for these elements. So sulfur, chlorine, aluminum, and sodium. Okay, let's see. We have sulfur, chlorine, aluminum. So we have sulfur, chlorine, aluminum, and sodium. So remember, they get smaller as you go across. And so it's looking for, did it say increasing or decreasing? It says decreasing atomic size. So that means we want to go to the biggest one first, which is going to be sodium. Sodium is bigger. So sodium is larger than or greater than. Then the next one we ran into was aluminum, right? Okay, and then sulfur, and then chlorine. Oops. So there's sodium, aluminum, and we said sulfur. Chlorine is the smallest, so that's decreasing size. So the biggest is sodium, going left to right, aluminum, sulfur, finally chlorine. Okay, 7, which element in each pair has atoms with a larger radius? And so basically we're looking at where these elements occur in the periodic table, and we're trying to determine which one is bigger. So sodium or lithium, let's take a look. So here's sodium, here's lithium. Sodium is bigger, it's got 3 rings. Strontium or magnesium, let's take a look. Here's strontium, here's magnesium. Strontium has 5 rings, magnesium only has 3. Strontium is larger. Carbon or germanium? Okay, let's see. Here is carbon, here's germanium. Germanium has 4 rings. Carbon only has 2, so germanium is larger. And then finally, selenium or oxygen. Here's selenium with 4 rings. Oxygen has 2. Selenium is larger. Okay, number 8, identify which group corresponds to each of its common names. Okay, so halogens. Halogens are located right here, group 17. These are the halogens. The alkaline earth metals. So alkaline earth are right here, group number 2. Here are the alkaline earths. The noble gases. Noble gases are right here. They're group 18. Let's see, the alkali metals. Alkali metals are right here. Hydrogen is not one of them, but these other elements in group 1. And then the transition metals. Transition metals are anything here in this center section. Okay, these are transitions. You could even include these down here. They're sometimes referred to as the inner transitions. But yep, transitions is basically this middle section. So we'll say groups 3 through 12. Okay, so next we're going to calculate the Z effective, which is the effective nuclear charge for the elements magnesium and chlorine. And so here I've given you the formula. So to calculate the ZF, the effective nuclear charge, you take the number of protons, which is the Z number, minus the number of core electrons. Okay, and so core are the ones that are not valence. So let's take a look at, like, for instance, the element magnesium. All right, and so if we look at magnesium here, here's magnesium. So you'll notice it has an atomic number 12, mass of 24. So what that tells us is that magnesium is essentially made up of this: 12 protons, 12 neutrons, 12 electrons. Okay, so I'm going to draw just kind of a Bohr model here. So let's say I'm going to put the 12 protons, 12 neutrons in the center. Okay, in that first energy level, you guys remember when we did this, we could have 2 electrons in that first row. Okay, and then after that, they want 8. So the first one has 2, then it goes 1, 2, 3, 4, and then they start pairing up 5, 6, 7, 8. Right now, we only have 10 electrons in our drawing. Okay, so I'm going to put out in this next level 2 additional ones. Okay, now there are the 12 electrons. You don't have to draw a Bohr model to solve these. I'm just demonstrating kind of how it works. So if you look at this, I want to know the number of protons. Well, it has 12 protons, right? And I'm going to subtract the number of core electrons. What you guys have to understand, these two aren't core. These are valence, right? So we've already talked about, so there are 2 valence, those outer electrons. So that means what's on the inside, what's in the core, well, there are 10 of them. Okay, so that's all the electrons. So there's 2 valence but 10 core. Well, we have to subtract the core. So this is minus the 10 core electrons. That means I have ZF's effective nuclear charge of 2. Okay. If I'm going to do the same thing here for chlorine, okay, let's take a look at chlorine. Chlorine's right here. Its atomic number 17, a mass of 35. So that means there's 18 neutrons, 17 electrons. So we have 12 protons, or not 12, I said 17. 17 protons, 18 neutrons, and probably 17 electrons if it's going to be neutral, right? These are going to be equal. I'm not going to draw the picture of this. We don't have to, because we know when you look at chlorine, because it's in this column, these all have 7 valence, right? Everything here has 1, everything here has 2, 3, 4, 5, 6, 7, 8. So we know that chlorine has 7 valence electrons. Or did I say 17? I don't know if I said 17. I meant 7. So hopefully I said 7. I don't remember. 7. So if I'm going to do this formula, so the number of protons chlorine has, it has 17 protons, minus, okay, well, if you look at this, if there are 7 valence, and there's a total of 17, that means I have 10 core electrons. Okay, well, if I'm going to take 17 minus those 10 core, that means I have a ZF of 7, effective nuclear charge. So what that means, so in a magnesium atom, like one of these valence electrons essentially feels the pull of 2 protons pulling it in. If I were going to draw the one on, if I was going to draw like chlorine, here's like chlorine's valence electrons, it's feeling the pull of 7 protons on it. So it's really pulling those electrons into the nucleus, which this is kind of why, we talk about atoms get smaller as you go across left to right. Okay. Okay, here's a table of successive ionization energies. So what information can we obtain from this table? Well, we talked about this a little bit in class. I demonstrated this. And so when you're looking at this like I1, I2, I3, I4, this is telling you how much energy it takes to remove 1 electron from an atom, a second, a third, a fourth, a fifth, a sixth, a seventh, okay? And so what you're looking for when you read this table, you're looking for a big jump. Okay, something where you have a large gap between the two numbers, all right? We're talking like 4 or 5 times or greater. So like if you look here between the first and the second, it's like 10 times the amount of energy. Okay, so that means you can strip away 1 but not 2. Well, that makes sense because sodium has 1 valence. Same thing if you look at magnesium, okay, we double and then, it's going up, like 4 or 5 times there. So we're talking about with magnesium, we could remove 2, but not 3. Okay, and once again, so what that means, if you look, like we just drew magnesium, so here's the nucleus, here's 2 in the first energy level, the next one has 8, right? And then that third energy level had 2 electrons in it. Well, it kind of makes sense, because if you look at magnesium, we can remove 2, but not 3. If I remove this guy, and I remove this guy, okay, now what do you notice we have? After you remove 2, you've got a stable octet, right? You cannot remove an extra electron from it. So that's why you see this big gap, in this section, because you can remove 2 but not 3. And the same thing flows throughout the rest of the document. If you look at chlorine, okay, less than double, 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 and it's over, well, I guess that's not the best example, but that's really kind of small. Well, I don't know. Don't look at chlorine as an example, but the other ones like here, look for instance like phosphorus. Okay, less than double, less than double, less than double, less than double, and then it's like, 4 times almost greater than. So once again, that means you could remove 1, 2, 3, 4, 5, but not 6. Okay, so it just basically tells you how many valence electrons there are. The only other thing I'd have you guys recall, okay, so I'm going to show you that thing with the trends again real quick. Atomic radii, okay, remember how we talked about how going down atoms get bigger and going across atoms get smaller, okay? Well, there were 2 other trends. First, ionization energy, so that's the amount of energy removed to strip an electron from an atom. Going down, it gets smaller. Going across left to right, it gets bigger. There was one other trend called electronegativity. That is the attraction for a shared pair of electrons in a chemical bond. So if you have two atoms sharing, which one pulls stronger? Its trend matches this one. So going down, the electronegativity gets smaller, going across it gets bigger. So if you guys understand these concepts, it'll answer a lot of questions on the exam. Okay? All right. Well, that's it.